Welcome to the Simulation Innovation Forum by our partner Technia. My name is Andreas Seidel. I'm around the simulation business for more than a decade now and focusing intensely on the topic of processes within the simulation domain for different physics and also multiphysics applications. Within the next around 25 minutes, I want to give you a heads up on the topic of simulation-driven design and how to speed up innovation. So first of all, why simulation? Why do we do simulation? And when we're looking at a typical development process, we usually have a scope of a project. So we have a kickoff and we want to achieve something in a given time. And any project is mainly driven by requirements. These might be requirements from a regulatory body like certifications, etc. Might be requirements given by your customer, by your OEM, or it might be simply basic requirements that are given due to your internal processes. The next big topic, big challenge is the topic of design. So you're going to pre-development, go into the CAD department, create the CAD data, etc. to create your virtual prototype. And then it comes to validation. And between design and validation, we usually see the first big gap. So within the design department, we are really good organized. We have nice data management tools, etc. But when it comes to validation, it's usually a bit decoupled. So either you go to physical testing, so you want to manufacture a prototype, then it takes time to manufacture the parts, to assemble everything. Usually you're not going for one prototype, but you need maybe several to get a level of certainty. And we have the really big issue. If that prototype fails, we have to redo it all again. We have to perform design changes. We have to go in the manufacturing again. And it simply takes a huge amount of time. And actually that's where simulation usually comes in. So we're doing simulation to analyze the behavior of a system. So we don't want to have a physical prototype that we need to manufacture. It takes really long time to set it up, to investigate on it. And especially if you want to do changes, iterations, it simply takes too long. So we want to leverage simulation to analyze the behavior of a system. And luckily, we're usually starting from design data, from CAD data. We can easily abstract it, do modeling to create a mathematical model. Sounds really complex, is really complex in the background due to really nice user interfaces. It's getting more and more easy. And based on this mathematical model, we can do simulations. So we can do our prototyping virtually based on simulation results. And when we're looking at the simulation in the development process, as is, let's take a look at the V model. It's really a simple setup. So we're going from requirements to system design components. It's usually where we're having the CAD department. And then the typical approach is to do the prototyping. So get into manufacturing, assemble everything, and do the test. And where we are usually using simulation currently, as is, state of the industry, it's really back here. So instead of doing this physical prototyping, simulation is used to cut these times and to try to speed up the process, to reduce the costs for testing, and basically just go to testing after in the simulation everything is valid, so you're sure your test is gonna pass. Now the title is Simulation-Driven Design. Is it really simulation-driven if you do all the design and then test afterwards? No, not really. And why is that an issue? It is an issue because when you finish your design first, the designer has put in days, weeks, maybe months of work or thought, putting in lots and lots of details. And in the end, he's passing it over to the simulation department to get the validation. So what's the simulation guy doing? He's importing the data, usually even data like step or other neutral formats. And the first thing the simulation expert has to do is usually heal the geometry. He has to remove many, many details because he doesn't need them. And then after days, weeks, he can finally get his results of the simulation, come back to the design engineer, and then maybe the design the simulation expert has been doing his validation on is already outdated. We might have new requirements, we might have 2 or 3 new steps or revisions of the CAD data. So we're really facing the issue that we're having too long turnaround times. And even if the results come back in time, if you have a detailed design and then you need to change something, it takes a lot of time. So we're getting severe inefficiencies with such a process. So the to-be, the ideal world, would suggest that we start with simulation really early. So I'm starting with my design. I have basic requirements, and even with really early stages of the design, with early concept phase, I'm able to run first simulations to investigate how is the performance, to be able to decide, do I go for option A or B, to really support the design process, not do validation afterwards, but drive the design by knowledge you're getting from the simulation early. And how this can be achieved, there are different ways. And one option is to go for really easy to use tools that the designer is using directly. So we're having here a short video where the design engineer is simply selecting his part. He can use a really simple role. It's called linear structural analyst. And he's having a guided workflow. So I want to do a structural simulation. You have the geometry here. Material properties are directly imported from the CAD. We're having nice pictures to explain to us what the boundaries are that we are specifying. And this makes it really easy to use. And this is allowing a designer to easily run simulations himself. It's not about the digits in percentage to achieve exact results. It's about getting an idea. How are my displacements, my stresses, where do I have peak loads, to better understand my design and to easily decide, do I want to go for option A, B, or C, if I'm having different ideas. So when we're looking into requirements for validation, so requirements we actually want to validate, we're having a bunch of different topics, disciplines that we want to investigate. Strength of our product, stiffness and eigenfrequency behavior, acoustics, thermal performance, electromagnetics, be it antennas or PCBs, flow behavior, like pressure drop, temperature mixing, etc. Manufacturability, of course, for plastics parts especially, but also for metal parts, and kinematics and kinetics. So we're seeing here we have a really big bunch of different requirements we want to check, and that we can check with simulation even in the early stages. I want to give you some examples of applications. So on the top left, we're having examples from mechanical engineering. There's a heavy-duty vehicle. So we are having structural requirements, like structural integrity, operator safety. So if the excavator would roll over, is the operator actually safe? We want to do cross checks with actual tests we're doing in the field to validate the simulation, etc., etc. Another example where we're leaving the, let's say, structures domain is the application of electric drives. So we're having flow simulation for thermal management. We have the electromagnetic performance of the electric engine. Especially in electric drives, the topic of noise and vibration is becoming huge because you don't have, like in a combustion engine, the steady sound and noise level that you usually have, but major acoustic interferences come from the gearbox, for example. And we have topics like gear lubrication. Similar examples are for electronic devices. So here we have PCB, we have EMC topics. We have thermal performance, again structural performance also. And another big topic is that of body in white and chassis components, especially in the automotive industry, where we're having huge sheet metal assemblies with welds and spot welds, etc., that we need to model and analyze. Many know Dassault Systèmes as a supplier for high fidelity structures codes like Simule Abacus, but actually our portfolio during the last years has expanded extremely. So in basically all physics, we're present with technology leading software tools. I'm going to dig into that later on. But first I want to give two examples, more detailed examples, that many people aren't aware of that we're having such solutions. The one is the example of gear lubrication. So with Simule Xflow, we're having a CFD code for multi-phase flow, for open surface flow, etc. It's based on lattice Boltzmann technology, and it's allowing really short modeling times and high fidelity, especially if you're having also moving parts, and especially for a gearbox. Even if you have a prototype, it's really, really tough to actually get any insight on the lubrication if you want to measure it, simply because there's fluid everywhere. So you can't really see anything within. And another example is the example of an HVAC system. So what we can do is we can simulate the airflow, and we can simulate it in a detailed way to actually make the sound visible and hearable. So what does this have to do with simulation-driven design? Well, fact is the following. We're having processes in place that are able or that allow the user, if he is consistent in the naming of his geometry, to run such analysis, such simulations by a couple of clicks of a button. I've been pointing it out before. Dassault Systèmes Simulia is not structures anymore. Dassault Systèmes Simulia portfolio is a complete set of tools, a complete set of processes to investigate different physics, structures and solids, electromagnetics, fluids, thermal and controls on different levels, even going down to physical or micro scale, material sciences, and then going up to the physical macro scale continuum investigations, logical and functional layer. And these different disciplines are all covered by technologically leading software tools within the environment. So for structures, we're having Abacus as the leading FEA code. For multi-body simulation, we're having SimPac as the technologically leading tool for multi-body simulations. FESafe is a highly rated tool for durability analysis. Wave 6 is the only vibroacoustics tool that's actually covering all frequencies and all methods, and at the same time providing really, really short analysis times in a modern interface. On the electromagnetic sides, CST Studio Suite is an absolute standard for anything that has to do with antennas. It is also strong in the topic of PCB and EMC applications, Opera for electric drives. On the fluids domain, we're having one of the most complete portfolios in the industry with the two latest Boltzmann codes, PowerFlow and XFlow, covering, let's say, extreme conditions regarding moving bodies, multi-phase flow, or extreme conditions regarding the precision on aerodynamics and aeroacoustics. With PowerFlow, it is even possible to get an WLTP certification for a vehicle based on simulation. So there's a really, really high accuracy of our solution that's even accepted and valued by the certification body. And of course, topics like automation and optimization are always a key part of the portfolio. So now we've been opening a big world of possibility, a big world of tools. But the title is simulation-driven design. And therefore I want to try to narrow it down again to get to the initial topic, let's say. So how can we achieve a simulation-driven design from all these different tools? And how can we achieve that efficiently? Because we have different, let's say, angles at doing simulation-driven design. It can be with tools that are simply very easy to use. It can be with tools that can be standardized. So it's a complex topic, but you make it easy to use. Or you want to have an expert, because you need to have an expert, but you want to have him closely in the loop. So these are the three different big topics we have. And to actually meet all the different approaches or demands, we need to have one thing, and that's scalability. We need to be scalable on the one hand in terms of functionality, and on the other hand, which is at least as important, on the topic of compute power. So what do I mean by that? Let's take a look at the FEA portfolio. So on the very left, we're having the structural designer role. It's been the role we've seen initially in the video. One of the guided workflow where we can set up a structural simulation within a minute or two. So here we're having a role that's really, really easy to use, almost intuitively. Really low level of training needed. Even if you're just using it occasionally, it's not really an issue. And that's also reflected in the pricing perspective. So it's also coming really cheap. So this is a tool where you can apply simulation-driven design in a way that you give your designers the ability to quickly check designs and design alternatives. This is extremely valuable, especially in the early design phases. Because if you're still in the, let's say, concept phase and you're trying to evaluate different options or possibilities, you don't want to send it over to the FEA department, for example, have to wait for days or weeks and then you get something back. No, you want to quickly set up a simulation. You want to get results within a couple of minutes and be able to decide option A or B. And we can scale this functionality easily because all these roles are using Abacus in the background. So even the smallest role, which is only doing linear FEA, has Abacus as a solver. The next level would be to get the full set of modeling, so mid-surfacing, shell meshing, everything that's in there, but you're staying on the linear Abacus solver. Then you can extend to the next level where you're getting nonlinear implicit solutions. So if you're having big deformation or you're having plastics that you want to model nonlinearly or rubber material, etc. And finally, the, let's say, big role, the mechanics engineer, where you're also having the explicit solver in there. So with that, you could even perform a crash analysis of a whole car, if you like. And the same role concept can be extended to the CFD domain. So we're having a fluid dynamics engineer role and a plastics injection engineer role, where we can check the manufacturability of plastics parts. One side remark: as soon as we're using one of those roles, we are automatically having a simulation process and data management system included. So in our solution, it's not necessary to purchase that separately or something, but that's something that's coming out of the box. The next level of scalability is the compute power. These basic roles here, they're having 4 cores included on the structures domain and 8 cores on the fluids domain. But whoever dealt with simulation knows sometimes you have a really tricky project or a really urgent project or whatever, and you can't just wait for the results. Or maybe you don't even have the hardware locally to simulate what you want to investigate on. And then starting discussions about an investment in hardware and additional software, etc. It takes basically forever. And many people would only go this way if they have really, really heavy pains. But what if we could easily access huge compute power, 1836, 144 cores in hard and software, and that for just a couple of €1,000. If you're having an urgent project and you tell the project manager, listen, we're getting in red in the project, we are late, by spending 3 or 4K euro, we could actually access a huge amount of compute power and make sure we have the simulation results for all the different alternatives we want to investigate tomorrow morning. This is where cloud compute comes in. I've been telling it initially, when it's getting to, let's say, more complex simulations, and you still want to use them in a simulation-driven approach, what you can do is use templates. So what we're seeing here is we have a CATIA assembly. It's been imported to the platform, and it's been set up with publications. Many CAD departments are working with publications. They're really, really robust in the process. And what we can do now, if we define the proper publications, we can simply load a template from the database. We have already an assembly in there. We want to replace it now with the current assembly. And by ticking OK and specifying a new name for the CFD simulation, we can easily load a template, in this case for fluids analysis. And we can now see in the background how the simulation is set up. So inlet is defined, outlet is defined, the fluids volume or fluid domain is defined, everything is meshed, and it's all related to the publications. So we're already ready to go. And with this, we can achieve an approach of simulation-driven design even for complex topics, where we provide these templates, these tools to the design engineers. Then we have even a third level, where it's getting to real big processes, where we can couple different physics and there again provide everything with a nice, easy and nice to use user interface. So to get to the conclusion, we're having simulation solutions for all physics that are out there. We can apply multiphysics simulation to link disciplines, so fluid and structures and thermal, etc. We are scalable in functionality, from really small roles, easy to use, up to full-blown abacus, CST, whatever you can think about. We are scalable in compute power. So if you're thinking about starting with simulation, and so far you said, yeah, buying software and getting hardware, etc., it's too expensive overall, you can start really easily by using cloud simulation. And even if you're already using simulation, really think about how much do you use your HPC? Are you reaching the limits of the HPC from time to time? Because cloud compute can really help here. And last but not least, we are providing simulation process and data management. And if you're using our pre-post within the 3D Experience portfolio, simulation process and data management is coming for free. It's included. So possible next steps. First of all, some open questions. Ask yourself, how long do I wait for validation? What is my cost of a physical test? How critical is it if a test fails? What does this mean for my project? Will I be running late? Can I still manage to be in time if my prototype fails? And also, how do you trace the relations between design and simulation? If you're saying, I'm all good in this, respect. If you're saying, yeah, well, there are some points that would ask for improvement, contact us to discuss a possible to-be process, to discuss where you want to be with your development process. And with this, I want to thank you for your attention. I'll be available for some questions now. And yeah, our nice if we closing slide. If we challenge the status quo, everything's possible. Thank you.